Okay, let us proceed from where we left, Master Science students. And uh, I mentioned that the aliphatic compounds or the compounds with single bonds, like uh, like alkanes, for example, uh, their structure is not rigid. So the group which may appear far away when it's in stretch form, when it bends, then the group which is far away can actually interfere with the functional group. So so there was a scientist who just said, "Hey, I want to study structure-activity relationship, but I want to rule out that effect of the groups which are further away interfering with with a functional group." So he decided to focus on the compounds having the benzene group. In this case, you are going to be looking at the benzene and then the groups which are going to be attached to the benzene and their influence on the functional group, which are going to call Fg. So in this case, there are atoms here which are labeled here, but I think let me mention something about the benzene. And and if you're going to have, let me see whether I can get a, a red pen so that okay, let me open it. Okay, right. So, if this is your functional group, let me see what is very clear. In red, yeah, good. So if that is your your functional group, the one which I put in the red box, uh, the carbon atom which contains the functional group is called the ipso carbon. Ipso carbon. It's called the ipso carbon. IPSO ipso. All right. And then I think the other positions they are very much mentioned. Like there is the author, which is the next to the functional group. So in a benzene ring, there are two ortho positions because there are two positions next to the functional group. And then the ones which are adjacent to the ortho, which are two carbon atoms away from the functional group, they are called meta. So there are two meta positions. And then there is one para position, which is four carbons are one, two, three, four carbon atoms away from the functional group. So the carbon bearing the functional group is called ipso. There are two ortho positions. There is two meta positions, and then there is one para position. Now, uh, when you're dealing with inductive effects, you're saying you're looking at the donation or the withdrawal of electrons along this carbon chain here, yeah, this carbon chain, yeah. So along the carbon chain, you're going to see atom A is going to be very close to the functional group. Then there is atom B, which is going to be next to the slightly far away, and then atom C is going to be it's going to be said to be far away. In fact, there will be very little inductive effect from from an atom C. Very little inductive effect. Yeah, yeah. So looking at steric effects. Steric effects, you're saying how bulky it is. You're going to see, excuse me, if you're going to have a bulky group next to the functional group, then that will interfere with the reactivity of the functional group. Assuming you've got something like a tertiary butyl group at position A, then it's really going to crowd around the functional group and may prevent, assuming it was something like a what, like a hydroxide group, then it may prevent it may prevent a base from abstracting a proton from the OH or something like that because they are crowding around the functional group. So sterically, the groups like A, they are going to be at position A, or it's the auto position are going to have an influence on the functional group. Then B will not have a big influence. No, it will have a moderate influence, but C, no, B and C will not have any steric effect because the benzene ring is flat, and therefore B and position B and C are not going to be anywhere close to the functional group. So sterically, it's only A which will have an influence. So B and C will have no influence on the reactivity of the functional group. Now, coming to the resonance effects, we are saying that inductively, no, for resonance, you're going to see that if A has got lone pair, or maybe it is electron, okay, if it is donating electrons via resonance, it's going to have an influence on the functional group at position at the ortho position. And the same thing will happen to the group at the para position. And once again, as I mentioned, when you're dealing with resonance, the distance does not matter, provided there is this conjugation, a double bond separated by a single bond, and then there's another double bond, something like that. Yeah. So when you're dealing with resonance, a group attached at meta position has no influence because the resonance they skip the meta position. So the resonance has an effect on position A and position, I mean on the ortho and the para position, but not on the meta position. Okay. So when you are going to study the reactivity of the benzene group, you're going to see you may, if you're going to be looking at a wide variety of compounds, some compounds may not have just something like the OH, or maybe, excuse me, or maybe hydrogen, but you may have big groups like you may have an amino group, it may have alkyl groups to attach to it, another groups which are large groups. So if you're going to really be looking at structure activity relationship, then you'd rather avoid the compounds with uh, studying compounds with any atom at other than hydrogen at position A. At position A, because in that case, sterically they're going to influence. They're going to influence the functional group, but there will be no influence on position B and C. And then, if you're going to be having uh, inductive effects, then you're going to see the atom or the group attached at position B is going to have a greater influence than position C. And if it is resonance effect, then the atom attached at position C is going to have an influence, greater influence on the functional group than at position B. So you can see, by eliminating putting the reactive or groups at the opposite at the auto position, and you're only going to focus on the meta and the para position, then you're going to see something about reactivity. In one case, the inductive effect is going to be greater at the meta position than at the para position. When you're dealing with the resonance effects, it's going to be greater at the para position than and there will be no resonance effect at the meta position. Yeah. So this is what led this scientist called Hammett, whom we are going to be mentioning later, to develop something like the Hammett equation, a very simple relationship of a logarithm, and it will tell something about if you're going to be looking at those field effects, the resonance and the inductive effects. So that's what made this scientist to actually focus on what? On the benzene group uh, having groups at the meta and the para position only, and nothing in the in the auto position. So in this case, he started by looking at the ionization of benzoic acid. The benzoic acid is just like a standard compound. So in this case, you're going to say you want to study how the benzoic acid is going to ionize in water. So the equilibrium constant, if I'm going to say that carboxylate is B, and then the ionized benzoic acid is A. So the equilibrium constant should be the concentration of B multiplied by the concentration of the proton over the ionized A multiplied by the concentration of water, which is 55 moles, which normally are constant. So you are going to see normally K equivalent times the concentration of water, which is 55 moles. It gives a new constant called Ka, so that the Ka will be the concentration of the anion times the concentration of the proton over the concentration of the ionized acid. Yeah. Okay. So once again, on this one, you are going to be focusing on the groups attached at the meta and para position due to the steric effect if a group is attached at the auto position. So in this case, you're going to see there is a general notation which you're going to be using. For example, you're going to say there's a group attached. Can you see there is the benzene group, and then there's a line or there's a bond in which it's not shown specifically attached at the meta or at the para position, but it's just a group like that one, somewhere in between there. So this is the notation which you're going to be adopting to say that you are showing a group is either attached at the meta position or at the para position, but not at the auto position. So that's what you're going to be using this notation to show a general structure in our structure activity relationship. All right. So the inductive effect, just to repeat on what I said, uh, it will be greater. It will be great if the group will be attached at the meta position, and almost nothing when it's going to be attached at the para position. By now you know that at the auto position it will be greater, but relative to the relatively, so at meta it will be really have a greater inductive effect and almost nothing at the para position. And then when you're going to have the resonance effect, uh, relative to the functional group, the group which will be attached at the para position is going to have a resonance effect on the functional group, and there will be no resonance effect at the meta position. Can you see that? Resonance uh, para position is going to have an influence, nothing on the meta position. Inductive effect, meta will be much greater than at the para position. Okay. So we are going to stop there, and then now we look at what this information can lead to what you're going to be calling the Hammett equation. Yeah, are we okay? So I think we'll just stop there and then proceed in a short while. Okay.